Chemistry students, Mr. Rosentes here, and I'm talking about Chapter 8, page 263, hybridization of atomic orbitals. The term hybridization should be familiar to us. When you take two different things and you blend them, you make a hybrid. And what we're going to hybridize are orbitals. We're going to hybridize S and P orbitals basically in this chapter. So I'm going to start with the electron configuration of beryllium. Beryllium, you should know, has an atomic number of 4. It's got 4 electrons. So the configuration should be fairly simple. It's got 2 in the 1s, 2 in the 2s. Well, this arrangement is satisfied. Not a lot of bonding here. What happens is that these orbits reconfigure. They change. And so I'm going to draw an arrow to indicate that they've changed. And what we change it to is an S and a P hybrid orbital. And in an S and a P hybrid orbital, that makes one of the 2s electrons available for bonding, and then one of the p available for bonding. So we've taken 2 from 2s, but 1 in s and 1 in p. And so now element like chlorine can share the hybrid electron. So BE would have, and Cl can share the hybrid new orbital. Right? So we call these sp, well, these are actually sigma bonds, but sp hybridized orbitals. So sp hybridized orbitals make linear molecules. Doesn't that make sense? There's not enough available electrons to share any more than 2, so it makes sense that it would just be a linear molecule. All right, let's try another one. How about the electron configuration of an element like, let's do boron. Boron, as you know, is 5 on the periodic table, so it's got 5 electrons. If it's got 5 electrons, we've got 2 in the 1s, we've got 2 in the 2s, and we have 1 in the 2p. 2, 4, 5 electrons. Now, we know that there's 3 more spaces in this 2p, and as I did earlier, the arrow indicates that we're going to reconfigure or hybridize. And what we find is that this is called the sp2, not to be confused with just the sp. The sp2 then opens up, and what we do is we separate these 2 in the s and hybridize them with the 2p. So now we have 1 in each, and hence making 3 possible sharing opportunities. So an element like fluorine can share the hybrid electrons. I'm calling these hybrid electrons. These are new. This is a new hybrid orbital here, and so we could share those. So we would have a configuration something like B sharing with F here, F here, and F here. And this is an arrangement that you'd find sp2 hybridized orbitals make trigonal planar or bent molecules. I wrote bend. Don't ask me why. Okay. Now let's try one more that we'll see in our chapter. And let's try the electron. There's several of these. We're just going to do 3. There's several more. As you can imagine, all the bonding possibilities are going to have different hybrids, but we're not going to go through all of them. Let's do the electron configuration of oxygen, and we know that the oxygen's 8 on the periodic table, so we're going to have 1s, 2s, 2p, so oxygen has 8 electrons, 2, 4, 5, 6, 7, 8 electrons, and so what we have here is we've got a sp3 with available electrons to share. Hydrogens can share now, and we have these would be lone pairs. This would be the water molecule, and we have sp3 hybridized makes tetrahedral molecules. All right, and it's tetrahedral if we look at the arrangement, including the unpaired electrons, because there's 1, 2, 3, 4 places where the electrons are shared with the oxygen. So, question: why do we find sp3 hybridized orbitals in pyramidal molecules? Well, because sp3 forms 4 hybrid orbitals, and pyramidal molecules, and then we'd have 4 orbitals that are being shared. 1, 2, 3, 4. So sp3 forms 4 orbitals. sp2 forms 3, and sp forms 2. So let's put that in a grid to summarize that information. Here's a grid that organizes that information. We have our orientations: linear, trigonoplanar, and tetrahedral. Those are the only 3 that we need to worry about. Atomic orbitals that mix, we have 1s and 1p that blend together. And the hybrid orbitals that are formed are 2. And they're 2 sp, and the orientation is linear, as I said. The second, trigonoplanar, have 1 s and 2 p's, and we have 3 sp2 for 3 orbitals. Therefore, we're going to get a trigonoplanar or bent orientation. And then lastly, for tetrahedral, the atomic orbitals that mix are 1s and 3 of the p's, because if you remember back, there was 2 of the p's. No, I'm sorry. This is SP is just 2 electrons. SP2 is 3 electrons, and SP2 is 3 electrons, and then finally we did the SP3 is 4 electrons that are shared. So we have 4 electrons or hybrid orbitals that are being shared for the SP3, and that's why we have this arrangement with 1, 2, 3, 4. Alright, and that's the tetrahedral arrangement. Alright, so what this does is this shows you how hybridization determines the molecular orbital, the molecular orbitals, and then in turn dictates the molecular shape, the three-dimensional geometry.